This chapter we will study about Thevenin theorem. Thevenin theorem is very important theorem because we need to know the Thevenin theorem very well. This is very useful, not only the circuit theory, but also the electron circuits. Maybe you will study in next year. This is very important and very useful, that the theorem to analysis the electric circuit and electronic circuit. What is Thevenin theorem? Thevenin theorem, I will read it a little bit. The concept is here. There are some circuit, voltage source, resistor, capacitor, and inductor, and current source, and resistor, capacitor, dependent source, and voltage source, and resistor, and inductor, and capacitor, whatever it is. It's a very complicated circuit. I don't know what is that. But anyway, it is a circuit, but it's very complicated. Then I want to know only some resistor here. My goal is to get the voltage over here. This is only my concern. I don't care about what is that. I don't care about what is that. My concern is only VO values. Then Thevenin theorem tells us that this complicated circuit can be replaced with only one voltage source and one resistor. Or actually, this is not resistor. This is an impedance. We'll cover about the impedance. What is that? But anyway, we call this impedance. In this level, because we just study about the resistor, then you can say this is resistor. R. And my target circuit here. So this is the Thevenin theorem. The Thevenin theorem tells us that the complex circuit, that we can transfer the circuit with only one voltage source and one impedance. So this circuit is very simple. So we can get our target values from the circuit easily. And that is the useful technique to analysis electric circuit. Thevenin theorem, the circuit is partitions into two parts, circuit A and B. This is their circuit. I don't know what is that, but anyway, the electric circuit and there another electric circuit. The circuit is connected to here. A and B is connected a single pair of terminal. They should be connected in this way here. Then Thevenin theorem tells us that circuit A is replaced by Thevenin equivalent circuit. We call this is a Thevenin equivalent circuit. Thevenin equivalent circuit. It consists of ideal voltage source and a series resistor here. So even though this circuit A replaced with Thevenin equivalent circuit, then does not change any voltage, any current of the circuit B, because that is, in the viewpoint of this terminal, circuit A and Thevenin equivalent circuit is exactly the same. So they does not give any things about anything about to the circuit B. So this is very powerful, because when analysis the electric circuit, So I constant is only circuit B. Then circuit A can be replaced very simple circuit with only one ideal voltage source and one resistor. Actually, this is not resistor. We will cover about the impedance in the next semester in the circuit theory second. And actually, the resistor is a sub concept of actually resistor is a kind of the sub element in the impedance. Impedance is of a huge concept to describe the elements like a resistor and capacitor and inductor. So anyway, this Thevenin theorem is very useful and very important things. To make a Thevenin circuit, we need to know about the Thevenin parameters. There are three parameters of Thevenin circuit theorem. The first thing is the open circuit voltage, and second thing is the short circuit current, and third thing is the Thevenin resistance. So the meaning of the open circuit voltage is we want to replace the circuit A with the Thevenin theorem. Then actually, I don't know what is that. I don't care about what is that in the circuit A. My concern is this circuit, how it looks like in the viewpoint over here. Because my concern is this point. In the viewpoint of this point, what looks like this circuit? So to take the characteristic over here, this, we need to know about what is the voltage of VAB when there are nothing. We call that, because this is open between A and B, we call that voltage is open circuit voltage. So when I see this circuit in the viewpoint over here, the voltage is kind of we call this is an open circuit voltage. Next thing is, when we connect A and B in short circuit, then maybe current flow in this way. Then what value of that? We call that is a short circuit current. We call that a short circuit current here. And third thing is the Thevenin resistance, RT. In this point of view, one looks like this element circuit A. We call that is a RT is a Thevenin resistance. Then we can define the Thevenin circuit is in this way. This is a VOC and RT. If we get the value and this value, then circuit A can be transferred to this, the Thevenin equivalent circuit. And the characteristic of VOC and ISC and RT is like here. VOC is RT, ISC. This is a characteristic between the open circuit voltage and the short circuit current, and then Thevenin the resistance. Okay, this is example 5, 4, and 1. There are some circuit here, and the problem is determine the Thevenin equivalent circuit here. So maybe this circuit will be transferred to the one voltage source and one resistor here. Then we know there is a VOC and RT. So to get the Thevenin equivalent circuit, we should get the VOC and RT. First, the the simple way to get the VOC is it looks like, we analysis this circuit the viewpoint over here. So what is the VOC? VOC is the voltage at viewpoint over here when the A and B is open. That means in the case the resistor voltage here in resistor 200 ohm will be VOC because this is open and we can get the VOC here. So first VOC, we can analysis this again very simply. 1 to 5, 50 times 200, then maybe that voltage will be VOC, and we can get the node equation here. Then we say this is VOC, then this current, to get a node equation we can define this is I1, I2, I3. I1 will be, actually this is 50, so I1 will be, this is 1 to 25 minus VOC divided by 50, and I2 will be 2 amps, and I3 will be VOC divided by 200. So based on the KCL in here, I1 minus I2 minus I3 will be 0. So we insert that value here. Then I1 is 50, 125 VOC minus 2 minus VOC divided by 200 will be 0. From this, we can get the VOC is 20 volt. And second thing is, we can calculate ISC, short circuit current. What is the short circuit current here? This is a voltage source, 50 2 amps and 200 AB, and this is 50 125. We can make this is a short circuit here. We call define is ISC. Then it's very simple because we define this resistor, then that value the difference over here is 0 volt, so this is 0 volt. Then we can ignore this circuit because this is a short circuit, it doesn't exist here. So because this is 0 volt, so the current over here I1 will be this current is 50 125, this is 0, so 125 minus 0 and 50. And so KCL over here is, because this is I2 and define this is ISC, so we make it here, then I1 minus I2 minus ISC will be 0. So ISC will be I1 minus I2, and I1 is 50 1 to 5 minus I2 is 2. So ISC will be this is 2.5 minus 2 is 0.5 ampere. So ISC 0.5. So VOC will be 20 volts and ISC is 0.5 ampere. So from here, we already know about the relationship between open circuit voltage and the short circuit current. What is that? VOC will be Thevenin resistance and short circuit current. So based on here, RT is VOC divided by ISC. And VOC is 20, ISC is 0.5, that means 40. So we can define that is 40 ohm and VOC is 20 volts. So this circuit can be replaced with 20 volts the voltage source and the 40 ohm is a resistor. Simply because this is a Thevenin equivalent circuit of this circuit. And to get the Thevenin resistance, we use the relationship between the voltages, open circuit voltage and the short circuit current. Actually, you can get the Thevenin resistor directly without this relationship. How to do that? I will give you a tip to get the Thevenin resistance directly here. The way to get the directly, to get the circuit here, and we want here the RT. It's very simple. What should we do? In this circuit, we change the voltages. I will give you an example. This is 100 ohm. Then what is the value of the resistance in this point of view? RT will be 100. And 100 and 100. Then in this case, what is RT? 50. Why? This is 100 parallel 100. It's very simple. And how about this is a voltage source? 100, 100. How about this? RT. That is a problem. It's very simple. To get the RT directly in the viewpoint of here is when circuit has a source, then when they have a voltage source, it makes short, and current source open. What's the meaning of that? To get the RT, the Thevenin resistance over here, we don't need to make any effect of the source over here. In the case of voltage source, we want to ignore the effect of the voltage source. That means the value of voltage source is 0. There are some source here, and that value is 0. What's the meaning of that? There are no voltage difference. That means there is a short circuit here. So when we want to ignore the voltage source, then you can transfer the voltage source as a short circuit in this way. Then you can ignore the voltage source, the effect. In the case of the current source, so we want to ignore the effect of the current source in the circuit. That means I source is V0. What's the meaning of that? There are current source here, then IS is 0. What's the meaning of that? There is no current through this element. Current does not flow anymore. That means this circuit is not connected. We call it open circuit. So when we want to ignore the current source, then we can replace the current source with the open circuit in this way. Then you can ignore the current source. Don't forget it. When we want to ignore the voltage source effect, then voltage source can be replaced with the short circuit. When we want to ignore the current source, we can replace the current circuit as an open circuit. That's a way how to see the selected circuit without any effect of the source. So in this point of here, this circuit, this is voltage source 1 to 5 and resistor, and current source and resistor, and this end point terminal is AB, and we want to see the circuit here in this point of view, so we can calculate the RT, only resistance effect of this point. Then how to then? There are voltage source here, so you can ignore that values. That will be 0. That means this is a short circuit. Then we can ignore this current source. What should we do? This will be open circuit. Then this circuit replace like that. Actually, this is 50. This is 200. Then we can redraw this circuit in this way. 50 short and 200, and this is A and B, and you can see this is RT. What is RT? Is 50 ohm and 20 ohm is connected in parallel. What is the value over here? This is 1 over 20 plus 1 over 200 and inverse. Then 200, 4 plus 1 inverse is 205. The value is 440. This result is exactly the same with that value. So when you want to design when you want to get the Thevenin equivalent circuit, you need to know about two values. What is that? VOC and RT. How to get that? To get here, we can calculate VOC and RT directly, or we can get VOC and ISC. From here we get RT. So this is one way. Or you can calculate ISC and RT. From here we can calculate open circuit voltage VOC in this way. So it depending on you, and based on the circuit you want to simplify using the Thevenin theorem, you can choose anything, any combination over here. This is another example. This looks like a little bit complicated because there are some the dependency source here. Because of that, it looks more difficult, but yes, it will be a little bit difficult, but it's not critical problem here. So determine the Thevenin equivalent circuit over here. That means you can make this circuit with only one voltage source and one resistor here. So we need VOC and we need Thevenin resistance RT here. In this case, actually, I want to recommend to get the RT not directly. I recommend to you that the RT by using the relationship between the VOC with RT, ISC. So I will try to get the VOC and ISC in this problem. What is that? Because the dependent source. Actually, at first, we'll try to get the VOC at first. Then what should we do? VOC is a open circuit voltage in this terminal, so it's very simple. I recommend you, when you problem the electric circuit, I recommend you to redraw the circuit. During drawing the electric circuit, we can understand the problems, and we can think about how to approach to solve this circuit. So I recommend you to redraw when you solve the problem here. Oh, it's missing here. This is a circuit, 5 ohm and 40 and 12 volts, and you define this is IA. Then voltage source here, the variable is depending on this voltage here. So we want to calculate, this is VOC. How to solve the problem? Actually, because this is open circuit here. This is open circuit here. Open circuit. So this current here is 0 ampere. So what's the meaning of that? That means you don't need to care about that resistor. 5 ohm. So the problem is more simple. You can make a super node in this pointer here. Then we define the current. This is I1, this is I2, and this is I3. So based on this super node, we can make a KCL. What's that? Plus I1 minus I2 minus I3 is 0. Then we can define I1 is 4.5 IA, and what is I2? To get, we define that is a VOC, and between this point and this point there are 12 volts. That means that voltage is VOC minus 12. So I2 will be VOC minus 12 divided by 10 ohm, because this is 10 ohm. Then I3 is same with IA. Then what is IA? I is current flowing through the 40 ohm. Then the voltage is defined VOC. So IA will be 40 VOC divided by 40. So we insert here I1 is 4.5 IA minus I2 is 10 divided by VOC minus 12, and I3 is minus IA is 0. Then we insert IA here. Then 4.5 40 VOC minus 10 VOC plus 1.2 minus 40 VOC is 0. Based on this equation, you can calculate VOC is 96 volt. So there is a result to get the VOC here. This is not difficult, because to get the VOC, we need to analyze electric circuit as you learned in the previous chapter, using the node equation or mesh equation. I told you before, node equation and mesh equation are kind of a great tools to analyze electric circuit as you given conditions. So mesh equation or node equation is a very great tool to analyze the electric circuit. So different equivalent circuit you require to get the VOC and ISC or RT. And to get these variables, we can use the tool to analyze the electric circuit, such as the mesh equation or node equation here. Next is I will get the ISC. I want to get the ISC here. So I'll try here. So I want to redraw the circuit here. This is a source, this is a voltpoint IA, and this is a resistor, this is 10 ohm, this is a voltage source 12 volts, and resistor is 40, and this is a 5, and then this is A B terminal we wanted to get, and we want to get the short circuit. That means we make a short circuit here, then redraw. This is ISC. So we want to know when the circuit is short, then how much current flow through the short circuit. That's the question. So that means we want to get the current of this current. I mean the flowing through this 5 ohm when the circuit is short. So this is another way, another problem to analyze this electric circuit. I mean the circuit is different. In the previous, the circuit is open circuit here. But this problem is, this is short circuit. This is a little bit different problem, different circuit. So anyway, but we will use the same approach using the supernode here. I will make this a supernode here. Then I will try to solve the problem at first. We can define this I1 and define this I2 and define this I3 and define this ISC. What should we do at first to analyze the volt here and define node voltage here? This is a V, how to say, we call this is a V C, and define this is a V D in this way here. Then what is the current of the I1? First we need to define the current. I1 is 4.5 IA. And what is I2? I2 is, this will define this is a reference node, VC divided by 10. And what is I3? I3 is VD divided by 40. And what is actually not 4, actually SC, that is VD divided by 5. Then we can make a K shell in the point over here. What is that? Plus I1 minus I2 minus I3 minus ISC is 0. So to get the value of the ISC, because we use the node equation, so we need to define, we need to get the VC and VD at first. So we're adding the old value of here, adding here. So we get I1 is 4.5 IA, and I2 is VC divided by 10, I3 is VD divided by 40, and ISC is VD divided by 5 will be 0. Now we have, how many variables are there? There are 3 variables, IA, VC, and VD. So to make up two more equations, then based on the supernode, how do we get that? We get the relationship between the VD and VC. VD, use the VD is VC plus 12. We need one more, the variable. Then what is IA? IA is defined, the problem is here. And IA is the same with I3. The I3 was VD divided by the 40. So we adding IA, VD, and actually no, I will get a VD. So from here the VC is VD minus 12. So not these values, we're adding VC in here and IA in here. So this equation can be expressed with only VD. So based on here, so you can calculate 4.5 40 VD minus 110 VD minus 12 minus 140 VD minus 15 VD is 0. So from here we get, from here we can calculate the VD, and then our target is not actually VD. We want to get the ISC. What is the ISC? ISC is VD divided by 5. So we get the VD here, and adding the VD here and divided by 5, that value is 96 divided by 85. That is the result. So based on this problem, this approach, we can get the values 96 divided by 85. So we write here VOC was 96 volts and ISC is 96 divided by 85 amps. Then what is RT? Terminal resistor is VOC divided by SC. Then that value is 95 ohm. So from here we can make a Thevenin circuit that will 96 volts and RT is 85 ohm. So we can replace this electric circuit with this simple Thevenin circuit. And next we'll study about the Norton equivalent circuit. This is Norton equivalent circuit. Actually, Norton's equivalent circuit is very similar with Thevenin's equivalent circuit, but the different thing is the Thevenin's equivalent circuit the very complicated circuit can make an equivalent. This is the same equivalent circuit with one ideal voltage source and the series connected resistor here. We call that is a Thevenin. But the same circuit can be expressed not voltage source but the current source here. And in this case, the resistor is connected in the parallel. So we call this circuit is Norton's equivalent circuit. So in this case, we express the voltages VOC and then RT. So in this case, the Norton's equivalent circuit is expressed the current source is ISC, and this is RT. So we call this is Norton's equivalent circuit. The relationship between the Thevenin circuit and Norton circuit is we already studied in the beginning of this chapter, source transformation. We already studied about here. The source transformation is what is the source transformation? We already studied here. We can transfer the voltage source to the current source, or we can transfer the current source to this voltage source. So what's the meaning of here? So we have the resistor here, and we have the source, the voltage source. Then we can replace the current source. So in this case, the viewpoint of here, this circuit should be the same. That is the source transformation. In the source transformation, we derive the relationship between when they have the voltage source is Vs and this is the resistor Rs. Then the relationship between the IP and Vs is the Vs should be divided by Rs, the values. That is the 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 current source, and Rp is the same with the Rs. You know, in the viewpoint of the Thevenin, the Thevenin, the equivalent circuit, I want to analysis this circuit with Thevenin, the equivalent circuit. You already study. This is a source and resistor here. Then we want to see this circuit with Thevenin equivalent circuit. The viewpoint over here, we want to calculate VOC and ISC and RT. What is the meaning of the VOC? VOC means it's open. We define this as a VS and RS. The viewpoint over here, what is VOC? VOC means this is open circuit, and in that case, the voltage over here is VOC. I mean, because this is open, so the current is 0. That means this voltage drop is RSI is 0 because I is 0. That means VOC is, VS is the same with VOC plus that voltage, VOC plus RSI, but because I is 0, so VS is VOC. So you can say VOC is same with VS. And what is a ISC? In this time, we will calculate ISC. What is ISC? ISC is a short current. We make a short circuit, and then the current flowing this way is ISC. What is ISC? Is VS divided by RS. Is divided by VS. And RT is VOC divided by ISC is RS. So then we make a source transformation in here. We define IP. We define is VS divided by RS. Excuse me. So in the viewpoint of the Thevenin equivalent circuit, ISC was VS divided by RS. In the viewpoint of the source transformation, the IP is VS divided by RS. That and that is the same. What's the meaning of that? In the source transformation, the equivalent current, IP, the parallel current, was short circuit current. So when you have voltage and one resistor here, that can be expressed ISC and RT the same way. So we call this circuit is Norton's equivalent circuit. So actually, the Thevenin equivalent circuit and Norton equivalent circuit is the same. So to get the equivalent circuit, we should calculate the three variables VOC, ISC, and RT. So it's not different between the Thevenins and the Nortons. But only thing is, you can choose the voltage source or the current source to make a equivalent circuit. The reason, what should we choose? That is depending on the problem. If you prefer to choose the voltage source, then you can use a Thevenin circuit. If you want to use the current source, then you can use the Norton's equivalent circuit. So this is a example, the 551. We determine the Norton's equivalent circuit. What should we do? We should calculate, anyway, to make equivalent circuit, we should calculate VOC, ISC, RT in this way. We need the two variable here. Then to get that, you can get that ISC directly, but you can choose to get the VOC first. Then based on the relationship between the VOC is RT ISC, you can get the ISC indirectly based on the VOC and RT. Here, I will try to solve the problem very simply. But in this case, we make a circuit in this way. This is a current source, and this is a resistor here. We define there is a ISC, and there will be RT. Then, what should we do at first? This is our first solution. Okay, I want get the variable. We make this ISC and RT. This is AB. Then the source solution one. What should we do? Well, first we can calculate the source circuit current directly. Then we can redraw. The circuit is 2 ampere, 40, 1 to 5 volts, 116. Now this is AB. And to get the ISC, what should we do? We connect directly. So we define this is ISC. We should know about the ISC at first. Then, because we currently directly in short circuit, that means we don't need to consider that resistance because this is short circuit. Then we have only two nodes here. This is one node, and this is two node. So define. I will make this is the reference node, and then define this is VA. So I define this is I1, I2, and I3. So I1 is minus 2 ampere, and I2 is 40 divided by VA, and I3 is unknown. I3 is unknown, but I3 is ISC. So actually we need to get I3, ISC. But based on these voltages, we can get the VA. What is VA? VA in 125 voltages and ground. So VA can be defined, okay, VA plus 125 is ground, 0. So VA is minus 125. So we add in here, then I2 will be 40 minus 125. So based on here, we can make a KCL in point node here. That means plus I1 and minus I2 and minus I3. SC should be 0. So ISC is I1 minus I2 and I1 is minus 2. I2 is minus 40, 125. That value will be 1.125 ampere. Then I want to get, next problem is so ISC is 1.125. And next we will calculate the RT. Then in this case, okay, ISC is 1.125 ampere. And next, so we want to get the RT here. Now, how to get the RT? In this point, there are the constant independent source. So to view over here, the current source is open circuit and voltage source is a short circuit. So that circuit can be redrawn because the 2 ampere is current source. This is open, so we can ignore here. So this is 40, and this voltage is short circuit, 98, and 160. Then there is RT. So what is RT? R is parallel and that values. So that value is 32. So RT is 32. So that means the Newton's equivalent circuit RT is 32, and there is 1.125 ampere. This is a way how to get the Newton's the equivalent circuit. Next, I will give you another solution. The second solution is this. We can approach the different way. We already learned about the Thevenin theory and Thevenin theorem and Newton theorem, so we can use it. Okay, I will redraw the given circuit here. It's 2 ampere and 40 and minus plus 125 and 160. So we make this Newton's the equivalent circuit. So to do that, if you see that point here, this is kind of a Newton's the equivalent circuit. Using the source transformation, then we can take that circuit can be replaced with another circuit. How to that? 2 ampere, 40. Then what is the VOC? Open circuit voltage is, what is that? That will be, because 40 flow here, so that value VOC is minus 80. So this circuit can be redrawn. Here. Then value is, because current going flow in this way here, so that value is plus. But we define that VOC is this direction positive, so this is minus 80, and this is 40. Why? Because it's the same. There is a parallel resistor and series resistor, and there is one more 125 and 160 ohm. That's a second. Then in the viewpoint of in this area here, this resistor, this source and this source is connected serially. So this circuit can be simplified. This is 125 and this is minus 80. The direction is the same. This is minus plus, this is minus plus. So this is simplified one voltage source. How much? 125 minus 80 equals 45 volts and 40 resistor here. Then this is 116. Right? Then we can also transfer that circuit with another current source out of that register, because this is 40, so this is 40 and this is 45 and 40, 45. Then we can make ISC with 40, 45, so 40, 45. Then we redraw the remaining circuit 116. Then what's that? That is 40 parallel 116 is 140. That value is 32. Then we can redraw this circuit is one current source and resistor here 32, 5, 40. That is 1.1 to 5. So this result will be the same with that result. This is another approach. Now, at first solution, we calculate ISC and RT directly, so we can get the values. The second approach, we can simplify the step by step in the here and here and next simplified and next simplified register, and we get the final, the simplified, the Newton's equivalent circuit. That's it. We can say what is a better approach to solve or analysis electric circuit in this point of here, but it depending on you, and you have preference then to what is better to analysis or approach or the study the electric circuit. So the important thing is you try to exercise the many electric circuit as much as possible. So based on that, you get your own skills to what is better to solve the electric circuit. The important thing is insight. You're based on the experience. This is another example to get the Newton's equivalent circuit. So they have the same problem we deal in the previous the Thevenin's theorem, but in this case we will get the Newton's the equivalent circuit. So our final goal is we make a current source in the parallel with the values, and this is the same because this is ISC and in the RT. So we should calculate that value in this way. So we will use the same approach here. Then first in this case I will try to get the V or C at first. Then I will redraw the circuit again. 4.5 IA 10 ohm. This to 1 12 40. This is 5 ohm. And then we define this VOC here. So because this is open circuit, there are no many here. So we define this is VOC. I will choose the super node here. And I decide to, this is a reference node. And I call that is a V1 here. Then define this is I1, this is I2, and this is I3. So what is I1? I3 is actually same with IA. So we'll eliminate that, not I3. I choose this is IA. So what is I1? I1 is 4.5 IA, and I2 is V1 divided by 10, and I3, actually not I3, is IA is 40, and VOC. Based on the supernode, we get the relationship between the V1 and the VOC. What is the VOC? VOC is V1 plus minus plus 12. So we can insert the V1. V1 is VOC minus 12. So that will be VOC minus 12 divided by 10. So we can make a KCL here. The KCL plus I1 minus I2 minus IA will be 0. So I1 is 4.5 IA minus I2 is 10 VOC minus 12, and IA is minus VOC minus divided by 40 to be 0. Then we have a relationship between that and here. IA is that is 4.5 40 VOC minus 10 VOC minus 12 minus VOC is 0. And here we got the VOC. VOC is 96. It's the same result we covered the previous problem. Then we next is ISC. Next ISC. ISC can be written in the same approach here. Now we'll redraw again. This is source circuit here. We define this ISC. This is 5 ohm, 40 ohm, and 10 ohm. And this is 4.5 IA. We define this is IA is 12. The same way, we also choose this is super node here, and define this is a V1. Okay, and this is V2, and we know the relationship between V2 is V1 plus 12, and you can get that is I1, I2, this is IA, and this is ISC, and I1 is 4.5 IA, I2 is V1 divided by 10, and IA is V2 divided by 40, and ISC is V2 divided by 5. And we have KCL here. So plus I1 minus I2 minus IA minus ISC is 0. And we have one equations and that equations, and we add the values here. Down here we can calculate ISC is 96 over 85. So we get here, we already know here the VOC is 96. So based on RT is VOC divided by ISC. So that value is 98. So that is 85, and this is 96 divided by 85. This is Newton's, the equivalent circuit. This is the way how to get the values. Chapter 5 and 6, the maximum power transfer. This chapter we will discuss about how to transfer the maximum power to the load. That is a question. But that means we have one load here. And this load wanted to get the power from the circuit A. This is kind of a supply, power supply, circuit A. Then my target is, as much as possible, we want power. We want RL, the load, want to get the maximum power as much as possible. Then what should we do in the viewpoint of the maximum power transfer? So what should be considered in the circuit to get the maximum power in the load register? So to do that, we transfer the circuit A to the Thevenin equivalent circuit in this way. Then analysis, this is again the viewpoint of the power of RL. So from there, we can get any conclusion about what should we do to transfer the maximum power to the load. The viewpoint of the load or viewpoint of the circuit source. Okay. Then we need to calculate the power. The power consumed by the load is written in this way. P power is voltage multiplied by the current. And here we define the current is I. And define the voltage is V. Then, because of the Ohm's law, the V is equal to the IR. So V is IR and I. That will be I square R. There is a power consumed by load. Then we need to calculate the I based on the DC circuit. If the circuit can be expressed with the Thevenin, the equivalent circuit, then I calculate, this is RT and RL is series connected. So RT plus RL divided by the source voltage is Vs. So we insert this current here. Then power is RT plus RL and Vs square and RL. There's this equation. So we can simply get the power in terms of what source voltage is. It is kind of an open source voltage, open circuit voltage in Thevenin equivalent circuit, and the load resistor and the Thevenin equivalent resistance of RT. So we need to know about the condition for the maximum power transfer to the RL. So what should we do to transfer the maximum power to RL? That is the question. So to do that, at first, in the viewpoint of the RL, what should we do to get the maximum power when the system is given? The the power supply is given, is fixed, because this is kind of the source is fixed. Then in the viewpoint of the load, to get the maximum power, what should we do to RL? So that is the condition for the maximum power transfer to RL in view point of load. So to get this condition, we can assume the source voltage Vs and RT. What's the meaning of that? The Vs and RT to fixes, that means the source is fixed. Then the power consumed by load is dependent on the RL. Why? This is a power equation consumed by the load, then Vs and Vt is fixed. Then the power consumed by load is a function of RL. So based on the RL, according to the RL, the power consumed by load is different. So actually, my concern is how to make a maximum power. That means the relationship between, if draw this figure, if draw the power, this is pi p is a function of RL, Vs, and RT. If this is a fixed, then function of only RL. So if draw the here, then this equation, that is Vs square RL plus RT square RL, and Vs RT is a fixed. Then this equation, this function, can be drawn in this way here. Because RL is a square here, so as increasing the RL, that will be this go to the 0. So we want to know that condition. When RL, what kind of condition of RL, the power consumed by load is maximized. So to get this point, what should we do? We can use this here is 0. This point is satisfy this condition. So because this is this is 0, the derivative value of the point is 0. So we can calculate the P in partial derivative of the RL. The result looks like here. So we need to figure out when that value will be 0. To get there, this value is 0. Vs is not 0, so we need to make that value 0. What is that? RL plus RT plus 2 RL should be 0. That means RL should be equal to RT. So this is a maximum power transfer condition. If there is a fixed, then RL should be same with RT. Then the power consumed here is maximized. That is a maximum power transfer condition. So the maximum power is P was Vs squared and RL plus RT and square and RL. Pmax means RL should be RT. Then that is maximized. So we insert RT here. Then Pmax is a free source voltage square divided by 4 RT. That is the result. So if you match that and that, the power is maximized here. So, and this circuit can be expressed with the Norton's circuit. So we can change that here. So even though that out is the same, but IS will be different. The IS will be Vs divided by RT. So in the viewpoint of Norton's circuit, the maximized power is expressed in this way. The RT and the short circuit means short circuit current square divided by 4. So this is a maximum power transfer theorem. This is very important thing. The maximum power delivered to the load by a source is attained when the load resistance RL is equal to the Thevenin resistance in the RT of the source. This is a very important theorem in the practical electric circuits. So we will later discuss about the matching. Maybe it will be done in the circuit theory second in the next semester. Then matching means, there are source here and several L capacitor, whatever it is, many things, and we get here. This is the receiver. This is not this is not applied to the power transfer, but also the signal transfer. This is a kind of a source. We want to transfer this source to the here, so we can measure the depth values. My concern is the input signal transferred to the output signal as much as possible. To do that, we there are many signal transfer line. There are many things like capacitor, inductor, whatever it is. Then, if to maximize the transfer efficiency to signal transfer, we have to make this impedance should be same with this total impedance. So this is a very critical problem in not only the power transfer but also the signal transfer. Okay, to check of that, we can solve some example. So if we have some source, the source is 180 volts here, and resistors like 30 ohm and 150 ohm here, and I want to get some power from the DC circuit, and my target is the power transferred to the source is maximized here. Then what should we decide RL? What value of RL get the maximum power from the source? That is a question. So to do that, we already know about the maximum power theorem. What is that? RL should be RT, the point of the Thevenin equivalent circuit. So we want transfer that circuit is 1 Thevenin circuit and V open circuit voltage and RL. Then RL will be RT. Then the power is maximized. Okay, then this problem transfer to about the maximum power transfer. This problem transfer to the how to get the Thevenin equivalent circuit. So circuit looks like here. This is 150 and 30 and 180. Then at first we want to get the open circuit voltage VOC. It's very easy. What is that? 150 plus 30, 150 and 180. The value is 150 volts. And next is we want to get the RT. How to get that? We want to get the RT here. To do that, the voltage source replaced with the short circuit. So this circuit can be, this will be short. 30 and 150, and this is RT. So RT looks like 30 parallel and 150. That value is 1 over 30, 1 over 150, and that values. So that will be 25. So this circuit, this circuit can be written here. Then that value will be 150 volts and RT is 25. So to get the maximum power in RL, what should we do? RL should be same with RT. So the maximum power RL is 25 ohm. That is and the maximum power, when the power is maximized, because at 25 we need to calculate the current I will be 150 and RT plus RL, that is 50, so 3 ampere. So P is I square RL, and RL 25, there will be 225 watt. That is the maximum power extracted by this load resistor in the given circuit. Okay. And next example is a similar example, but find RL for the maximum on power and determine the Pmax in delivered. The circuit is a little bit different, but anyway, our target is same. What should we do? To get the RL values, we need to make a simple Thevenin circuit. This is RT and VOC, and this is RL. And RL should be same with RT for the maximum power. So the problem is changed from the maximum power problem to the Thevenin equivalent circuit problem. So what should we do? At first, I want to get the open circuit voltage for this in the circuit. What should we do? This is 60 volts and 6 ohm and something here and here. This is 4 and this was VOC. Then because AB is here, 2 VOC. That's a problem. So we need to calculate the current. We decide this current is, I decide this current is I. Then VOC is this, because this is 4 ohm, it's 4I. And what is I? There are two sources here. One source is 6 volts, second source is 2 VOC. So I will be, the voltage is 6 plus 2 VOC divided by 6 plus 4. That will be 10, 6 plus VOC here, 6I. From there, I is 3. That means here VOC is 12. We get VOC. Then next is the we want to get the RT, but in the case of the dependent source, I recommend it to get the not directly RT, but to get the source circuit current. Then from the open circuit voltage and the source circuit current, we calculate RT. So the circuit can be written as 60 volt and 6 ohm. There are some voltage here, dependence to VAB, and we make this a short circuit here. That means the 4 ohm is now not anymore. So change here. Define this ISC, and that VAB, because it is short circuit, VAB will be a 0. Because VAB is 0, so that value is 0. So we can ignore that. So ISC will be 6 volts divided by 6 ohm. So 1 ampere. Therefore, RT will be VOC divided by ISC. So that is VOC is 12 and ISC is 1. So the RT is 12. So that was 12 volts. And that was the 12 ohm. So RL should be 12. Then the Pmax will be 12 and the current square, and the current will be 12 divided by 24 square. So this is 3 watt. So when we choose the RL is 12, the maximum power is 3 watt. That means we have the power supply in this way here. Then the maximum power to get from this circuit will be the 3 watt.